Can you see the screen?
I can't.
Okay, is it quite legible, or because I had to kind of fit it in the screen size?
I can see most of the square, if that's what you're talking about.
Yeah, so it's not too small, I suppose, right?
No, that looks fine.
All right, folks, so just a quick note. So I have given a small extension. Hopefully that helps for the project part 1. The part 2 is simpler than part 1, and that's why I had given a less number of days. But make sure that if you don't need time for part 1, get started on the part 2. You can actually work together on part 1 and part 2 and just bring part 1 to a very good point, and which you are satisfied with, and then go ahead and submit it, and then move on to part 2. The only other thing that is going to run in parallel with part 2 is going to be last homework, which will be given, I believe, on Friday or so. And it will have 2-3 questions, and it will be due at end of the semester along with the part 2. So you'll have a good bit of time for that. And it is, of course, just paper and pencil homework based on the dependence analysis, mainly the dependence tests and loop transformations and so on, so that we are ready for this particular part for the exams. So that is the main goal of that homework, so that we understand and apply these concepts. So with that, I'll get going for our rest of the stuff, which we are going to complete. As I said, the dependence analysis, loop transformations, all this topic will be a part of the last homework. But after that, we are going to look at some machine-specific optimizations related to mainly register allocation. That topics, those papers and that topic will also be there for the finals, but we won't have any time to do any homework. But hopefully it is okay, because you have done register allocation in your earlier classes and are familiar with it, and this is a machine-specific application. So hopefully we won't need practice on that. But if you have any questions, of course, we can take those up anytime and during office hours and things like that. I'm going to leave maybe a class or so just to discuss if you have any questions, exam overview and review and all those kinds of things. So we can always visit some of these things and anything else that you would like to, which may not be adequately covered in the homeworks. And feel free to ask questions. That's the whole idea. It's unfortunate that we are doing this remotely, but I hope you can always interrupt, raise your hand, and Nathan will monitor the chat. I can't see it, but I'll be happy to interrupt and answer it quickly. And then I typically pause for any bigger questions that you may have. You can certainly ask me that time or come to office hours. So all these are possibilities. And with that, what we'll do now is we'll continue our discussion about Banerjee inequality, which is called as also the Banerjee-Wolf test. And we were looking at the formulation of this. So we typically have a loop nest here. As we can see, there is an array X, and f of I is index function, which maps the iteration space 1 to n onto the array space in the right sense. And g of I is similar function, a different one, which again maps the iteration space into array space. X of f of I is a write and X of g of I is a read, and therefore we can test for different kinds of dependencies if they exist within the loop nest. Again, the idea here is to be able to see if the dependence exists. And typically, because of the regular nature of these accesses, most of the accesses here, by the way, like f of I and g of I, are linear functions, as you will see later. If there is a dependence, then it tends to be there in a repetitive manner. Let's say every fourth iteration there is a dependence, things like that. So it's not that it's one-off, it's there for just one iteration in the rest of the loop. It doesn't have dependence. It's rarely is the case. And we'll look at certain other variations of these. In that case, the dependence distance itself could vary, and in such cases, we can undertake some transformations. So the dependence may exist for a part of the iteration space, let's say half of the loop, and then suddenly might go away because the distance becomes very large between read and writes, and therefore the later half of the loop we could parallelize. I'll get into some examples regarding to this. So again, we are interested in if f of write iteration and g of read iteration become equal. So that they map onto the same array location during the execution of the loop. And as you can see here, IW is less than equal to IR, and that defines this is a flow dependence. Similarly, the anti-dependence case, you can see here again, both of these functions must be equal to each other, and the read must occur before the write. So the value of this g of ig at iteration space ig must be equal to f of io, which is the read, the write, and the read must occur before the write. So ig must occur before io. And then the last one is the output dependence, wherein there are two iterations, and it's similarly defined. So we were looking at this iteration space itself executes, as you can imagine, in the I1 going on from the outer loop being fixed, and then all the inner loop iterations executing, and so on. And we can enumerate these I and j, these functions. We can generate these the actual indices, and we can find out if they are equal to or not. And that would be a very naive way of doing this. And we can check if there is a dependence or not accordingly. But and this is what we call as this IP calculator, integer programming calculator kind of an approach, whereas it enumerates this and finds out if it actually finds out these if these two are equal. And it's a very super expensive method. Sometimes even n is symbolically not known to us, and it won't work in general. So so what we want to do here is be able to calculate either the dependence distance or direction vector, and then find out if there exists a dependence, that kind of an approach. But in general, what we will do is we will try to solve these dependence problems using what we call as dimension by dimension dependence testing. And we will try to see if the dependence is there in a given dimension, and if it is there, or if we cannot say it is not there rather, then we assume there is a dependence. Many times we cannot really say if there is a dependence at compile time. As in the examples last time when we saw it. And if we cannot prove there is a dependence, we have to assume there is a dependence, because otherwise the transformation will make the program illegal in terms of it will violate the memory semantics of it, and therefore it will not be right. So in short, the safety condition behind the dependence is that if you cannot prove independence, then assume independence. So what we do here is we call this as a dependence detection using direction vector oriented testing. And so if you assume a two-dimensional sort of a case here, you can see that these are the different possibilities that might exist for the dependence to be there. As you can see, that the equal to greater than is legal dependence. It cannot occur because of a normalized loop which is going from 1 to n. And so so the dependence here will be carried by the innermost loop, and it will be carried in a reverse way, and the loop doesn't execute in the reverse way. So that is impossible. And similarly, the dependence being carried by the outer loop by greater than vector is also illegal. It's not possible. So we leave out these two. After doing the normalization, these two directions become impossible for a dependence to occur. And we test the rest of them in terms of testing for a specific dependence. Sometimes what we also do is this, that we just test for star star. That means without assuming any dependence direction vector or any constraint on the underlying iteration space variables, we'll just test the dependence. So if there is no dependence in this unconstrained space for star star, there is no dependence whatsoever for the any of the other subvectors of these or direction vectors. So we can rule out the dependence right away there and prove independence, and we don't have to test anything below it. However, if we check that there is a dependence in star star, then maybe we would like to know for certain purposes what kind of dependence it is there for transformations and so on. So we can then probably test for a very specific direction vector. For example, is it less than? And if it is that way, then we can carry out certain transformations. Typically, the big problem about transformations is this, that the dependence of less than greater than is a problematic dependence, the one which I just highlighted here. That dependence does not allow interchange, as you will see later, because again the dependence is carried by the outer loop here and is enforced. And when we change that in interchange, greater than becomes the outer loop, and it changes the direction of the dependence from it will be now carried by the outer loop, and the direction of the dependence will change from maybe a flow to an anti, or anti to a flow, and why it will lead to semantics violation. So this is a problematic one. So for example, if we find that there is a dependence in star star, next thing we might just want to test is it of less than greater than? And if it is of that nature, then we want to undertake some transformations which are related to this, which is about interchanging. One of the transformations is called loop skewing, which allows you to change the vector or manipulate it. So in other words, specifically, we may not be interested in finding out all these different types of direction vectors, like less than, equal to, less than, or equal to. The reason is this, that for many purposes, for loop transformation, they are all similar, except for the fact of this less than greater than. So again, to summarize, we'll do a undirected directional vector test first, and we'll find out if that gives us independence. We're great, we're done. We don't have to do any of the internal tests. Otherwise, we'll do mostly less than greater than test and figure out if that is the nature of dependence. And then based on that, what the result we get, we will undertake some kind of a transformation based on that. So the dependence analyzer, as I mentioned earlier, is not done using IP calculators. The times during which this particular area was developed, we also did not have solvers and all that. Right, do have solvers which can scale, which can solve very large problems of integer variable in an exact manner. But during those times when the dependence analysis was developed, there were no such solvers, and yet I think they came up with very elegant and very useful techniques, and which were also quite accurate, as you'll see. So what are these different things? And it was all driven by empirical observations in terms of what is the kind of nature of subscripts that we see in most applications that we're interested in parallelizing, and the applications of those times and even now which continue to be there, were either image processing or scientific codes or simulations, HPC codes. And so they had not only linear subscripts, that means the array expressions, like here you see I plus 1 is a linear function of I, for example. Not only they were like this, they also had some even more simpler characteristics. And based on those, different kinds of dependence tests were developed to pick up all the common cases and then leave the hard ones and maybe do some approximations and so on. So right here you can see that there are such cases in this example. So we have a zero index variable subscript case. So for example, what we're doing is we are looking at these two references of A inside the loop, and we are comparing the dimensions, each dimension, to see if there exists a dependence in that dimension or not. If we can prove an independent dimension, we are done, because obviously for the dependence to exist, we must have a simultaneous dependent in each dimension, so that we are able to write at the same point to the particular array location and then read from that location. So for example, if we compare 5 and n, and by some analysis which we have figured out that n must be greater than 10. So here, through interprocedure analysis, we figured out that maybe n is greater than 10, and so this particular 5 cannot be equal to n ever. And so we proved the independence right here. And so this kind of a test is called as zero index variable tests. Many of these parameters, such as which are sent across the functions, which set up these types of equations and say solve them, or recurrences, they solve them. They set up these values of n and so on, which are passed into procedurally. So we might do some analysis in interprocedurally, find out the value of n and prove this. We could also put a simple test on top of this loop saying that if n is not equal to 5, then execute a parallel version of this, because then we are guaranteed that the first dimension never equals its counterpart in the read-write sense, and so therefore cannot be dependent. Even though the second ones and third ones can become equal, since the first one is different, it talks about a different location in the array and therefore no dependence. So there are many such cases of ZIV. The other one is the second dimension. Look at that, I plus 1 and I, and it involves only one loop variable, which is I, And again, a very simple expression based on it. And we can try and solve this very quickly. There are sub cases here which we'll talk about. So this is called a single index variable things. So each dimension therefore deals with only one variable, and so we don't have this complication of trying to see what happens for different variables such as I and j. However, the third one is more difficult, and it involves two index variables. It is called as MIV. J and K are the variables, and for that we'll set up some dependent system and we'll try to find out a little more details there. So let's go to this SIV case and separate it into two further parts. So you can see that in this example, this I, which is appearing here on line 10, this doesn't appear in any other dimension. So in other words, its solution is an independent variable as far as the simultaneous satisfaction of different dependent system is concerned. Again, remember that we must not only have first one equal, the second one should also be equal, and third one should be equal at the same time. So simultaneous solution should exist for the dependence to exist. However, J can be independently solved here I can be independently solved because it doesn't participate in any other system, and so this is called a separable SIV subscript. Now, this second and third dimension also have in the second dimension we do have J, but that J is also appears in the third dimension, and so it's a coupled subscripts. In other words, we must reason about simultaneously solving second and third dimension, and that's a complication. Because again, our goal is solve it in each dimension separately as much as we can and prove independence if we can. And if we do, then just halt there, because then there is no dependence, and move on to the next pair. So in this case for J, we can't do that. We can't simply solve second dimension, because the value of J that satisfies second and third dimension simultaneously really proves the dependence. And if we find a value which satisfies second dimension, that value doesn't satisfy third dimension, for example, to become equal to K, then that's a false positive. That's not a real dependence. That's a false dependence, because second dimension will become equal to another pertinent dimension of the read and write, but the third dimension will not become equal, and therefore they will write to two different array locations, and therefore there's no dependence. So I guess fortunately we have lots and lots of subscripts which are separable, and we are able to just tackle them. That's what we'll look at first. So let us look at separable SIV subscript. And the most general form of it, which in the linear form which occurs, is AI plus B kind of thing, as you are seeing here, or CI plus D kind of thing, which as you are seeing on the read side. So in short, we have only I is participating in only the dependence equation in the first dimension, and the linear function, the function which is mapping this I into the array space, is not only a linear function, but it's basically something like of this form, A of I plus B. So it's a simple linear function involving one variable, as you can see, I. And that happens to be a common case. And now our dependence equation would be AI times IW plus B, which is the reference generated on the right side, is equal to C times I read plus D. So if we can find IW and IR values subject to these constraints, then there is a dependence. If we cannot, there is no dependence. Now, further subcases here. So many times you'll see that the way the physical systems and spaces are modeled and so on, the coefficients A and C are the same for such systems of equation. Again, quite empirical observation, but you can see how it kind of leads to a very good and very efficient solution, which is the important thing here. And this occurs again a lot, that A is equal to C, the coefficients of the array, the loop index variables are the same, which map them to the arrays. So if you rearrange these equations based on A is equal to C, you can see that IR minus IW is equal to B minus D by A. Now you can see that we know that IR and IW and all are in the integral spaces. In fact, in the normalized integral spaces from 1 to whatever upper limit. And so their differences, whatever they are, must be also integral. In order for this equality to hold good, that is the dependence to hold good, we must have a situation in which B minus D divided by A is also integral. So in other words, if B minus D cannot be divided by A as an integer value, then there cannot be a dependence. So, however, if B minus D is divisible by A, and there may be a dependence. Now, what is the second condition which is at play here? And the second condition which is at play here is this, that IR minus IW is giving us some kind of a distance vector between the iteration which originates the dependent and the iteration which has a sink for the dependence. Now, if this distance is greater than the loop bound of I, then again there is no dependence. If it is, let's say this distance was 100 and the loop executes only 50 things, then you can see that the starting and ending iterations which carry the dependence, they are not there in the loop space, and therefore again there is no dependence. So two conditions are important here. One is A divides B minus D, and the second one is the right-hand side, which is telling us the dependence distance must be less than the difference between the loop bounds for I, upper bound minus lower bound. So I hope this is clear. If one of the conditions is not satisfied, there is no dependence. So that's how we apply these tests, and we are able to do it pretty well. About 37% of the cases are these SIV situations like this. This is also called a strong SIV condition because it has the strong condition like A is equal to C. Any questions about this part? Why the two conditions and so on? I hope it's clear. Okay, so if that is the case, then let's move on to the other one. So the next condition is many times we do have this equation like this, but one of the two, A or C, is equal to 0. That is, the subscript I is just not present in the other dimension. The coefficient of that I is 0. So by generality, if we just assume C is equal to 0, then the equation will be equal to IW is being given by B minus D divided by A. Okay, and so in this case, now you can see again D minus B must be divisible by A because otherwise IW will not be an integer which it is in our dependence problems. We have seen that is the case. So, and the second condition is very similar, that it's now pinpointing to a given particular iteration, and if that is not within the bounds of I, then again there is no dependence. So if IW is given by this, will be over the loop bound of 100, then there's no dependence, or if it is below the lower bound, there is also no dependence. Of course, the lower bound in all the cases is the normalized one equal to 1. So the dependence is there with a very large distance, and so this can be eliminated by using some transformation on the loop. So what is going on here? Maybe the dependence distance in the previous one, or this particular IW, that is where the dependence exists, could be occurring maybe in like 25th percentage of the loop. So that particular part could be executed sequentially, and then the remainder one, where the distance falls, becomes larger and goes outside the bounds of the loop, we can parallelize it. So I will come to that again, as I said, when we do the transformations. But let's keep going. Now we looked at strong and weak. Now the general SIV test. So which is something like this: AW plus B is equal to CI plus D. And there are multiple approaches to deal with these things. One of the approaches is to take this approach, which is shown here, which is usually, again, driven by empirical observations. A and C, which are the coefficients, are usually small values. Now, for every such pair, A and C, between 1 and 5, which is sort of what is typically observed in scientific course and so on, we could build a table, and each of the entries could be GCD of A and C, and then the second would be corresponding to this GCD, a solution to this particular equation, which is assuming the GCD is such and such. So you can see here that one solution to this equation could be equal to A times IW and C times IR, which is equal to GCD of those. And if the GCD does not divide D minus B, there is no solution. Otherwise, there is a solution which is given like this. And the general solution will be given by the following equation shown there. So we can find out if there is a general solution, if there is no solution, or if there is only one solution, and then quickly determine, as per what we get for the corresponding A and C, particular case covered here, and declare whether there is a dependence or not. This case is quite rare as compared to the previous two, and strong SIV and weak SIV are mostly the ones which are used. Instead of this case being done in this way, which can be expensive. Many compilers also adopt the broader result of Banerjee inequality, which I will get into very soon. So, but before we do that, let us see how to deal with simultaneous solutions to these coupled subscripts business. As I said, we had to solve when there are coupled subscripts. We can't do dimension by dimension testing. That is in this particular example. We can't solve for whether f is equal to h with the corresponding index vectors and then independently solve g is equal to k because we will get maybe dependence in each case, but if we do a simultaneous dependence testing, there may not be a simultaneous solution to this. So we could get a false positive there because of the solution in the first dimension cannot be being simultaneous with the solution in the second one. Again, I and j are participating in both dimensions, so that's why they are simultaneous subscripts. So, or coupled subscripts rather. So what do we do in such cases? There is a way to transform this system into one system by multiplying this by a particular coefficient and then add it to the other. So for example, if we have originally G is equal to K system, then we can see here that we can scale the first system by a factor of C and add it to that. And now look at this particular one system, which is C times F plus G being equal to C times H plus K. And if this gives us the dependence, then maybe we should assume a dependence on the previous one. But obviously now we are approximating. And if we carefully, however, choose this C, we can still be positive. And this is called as Lagrangian multipliers. We will not get into that much, but that is how the coupled subscripts are typically tackled, by choosing the right coefficients, right multipliers, converting into a single system, and then applying Banerjee inequality on top of it. So the case of previous one, this like where there are no strong or weak SIV case, as well as this, and then even when we have multiple index variable per dimension, that case, which may not be a coupled one, all of these are tackled through the Banerjee inequality. So that brings us to this, which is a very important test, which is used in practical compilers. And let us first look at the setting of this, and then we will try and do some analysis based on this and to see what is being approximated here and so on. So again, looking at the dependent system, let's look at it in a simple case, which is that last case, which was not a strong SIV or weak SIV. Use that as a starting point here. And we could have multiple I's and J's also in this. We need not have just one I or one J. So all those cases which were there in previous slides, they are being tackled here in general. So we had 2i plus 3 and I plus 7 as the two functions. And we are trying to see if there is a flow dependence from IW to I read, wherein this is satisfied, this equation is satisfied. And if you carefully look at it, of what is going on is this particular equation, if you rewrite 2iw minus ir minus 4, if you bring out all the things on one side, that becomes the equation. And the question is whether this particular equation H of IWIR embraces the value of 0 as an integer point within the region R. Now, what is the within the region R means? You can see that IW and IR both have constraints on them, that both of them are greater than 1. But less than 100. So you can see that this is a polytope between two variables of square rectangular kind of square shaped. And what we want to do is if this particular function 2r IW minus IR minus 4 becomes 0 on that. So this might be better illustrated if we go to our favorite whiteboard here. Okay, so let us look at what we were doing here and looking at the geometric interpretation of this, and then we'll see how that is being approximated here. I'm going to sketch this. So to begin with, we have IW and IR, and those are bounded, let's say by 1 to n. And then we have some function of C1 times IW minus C2 times IR minus, let's say, some constant D is equal to 0 or not. So geometrically, you can see that this is how it will look. These will correspond to this rectangular shape in the integral space. We call this as polytope in general because this is 2-dimension, but in general it could be n-dimension. And there are all these integral points which I'm showing as dots in the space. Now, if you really carefully look at this one, this is determining a line which has certain slope and blah blah blah. So I'm just going to draw this line like that. So this particular line, the question that we ask ourselves is this, that this particular line, does it have an integer solution? In other words, does it intersect this kind of an integral point in this space? This is maybe my IW, this is IR, this is my N, this is my 1, this is my 1, this is my N. So you can see that IW is bounded here within this and IR is bounded, and that defines this grid of integral points here. And this line is representing an integral thing. So it is, of course, I have shown it as a continuous one here, but it's not. It evaluates to integers, as you can imagine here. Question is, within this, does this line intersect some specific values of IR and IW which satisfy the lines equation, as well as which satisfy these constraints? And whether this grid point exists or not, that is the question. Could be that this line, and I'm drawing this separately here. So these are maybe these grids, right? Like that. And it may be that this line just manages to bypass all of them. And therefore, it does not have any integral solution in this particular space. And if it does not have integral solution space, then there is no dependence. However, if as shown on the left hand side here, it does goes through actual grid point, then there is an integral solution. Okay. So now this problem of determining whether the line hits a grid point or not is NP hard, and it's very difficult to solve this in polynomial time unless we enumerate and do blah blah blah, all these kind of things. However, this problem of whether the line as a satisfying solution in the underlying real space is easier one, much easier one. And Banerjee inequality targets this. So you can see now that the real space is a relaxation of the integer space. In other words, if we do not have a solution in the real space, if there is no solution to this equality in the real space, how can that be? That could be like this. Then this real space is, I'm drawing it here. And this is my real space. Okay, and this shaded space is my real space. And this particular line, whatever this is my big, this thing. And this line, especially at least during this interval of these IW and I, whatever these functions are, for these things, this line just does not intersect this space. This line, carries out some values for whatever reasons, and these values are over here, let's say. Okay, for the underlying values, this particular line just doesn't intersect this space. If that is the case, then there's no solution to this equation within the constraints of these. And we'll see some examples of these. And if that is the case, there is no real solution, and therefore there cannot be integral solution. And that is what the basis of Banerjee inequality is. That the values which are realized by this particular function, they are not, they do not intersect this particular space. So there is no real solution to this equation given these constraints, and therefore there is no solution. But however, you can imagine that in case the Banerjee inequality says that yes, there is a real solution, that means this line intersects. You can see that there are so many solutions here now that this line intersects this space, and there is a real solution to this particular equation. What does that mean? Does that mean that we have an integer solution? No, it does not imply that. And so that's a false dependence. So Banerjee inequality, when it says there is no real dependence or there is no real solution, it is quite clear that there cannot be integer solution and there cannot be any dependence. So it can prove independence conclusively. That it can say that, hey, in this case, there is no solution to this equation, and therefore, in the real space, and there cannot be any solution. So it is conclusive there. However, it is not conclusive in the sense of when it declares that there may be a solution or there may be a dependence. It can only say there may be a dependence because it says, yes, there is a real solution, but I cannot tell you if there exists a corresponding integer solution or not. So it only says maybe dependence or no dependence. So when this Banerjee inequality is not satisfied, it says no dependence, and that is conclusive. So we are safe there. So it asserts that there is no dependence, go ahead, parallelize, we are safe there. But we might have lost opportunities for parallelization. It may say that there is a real dependence, but there is no integral solution. And so correspondingly, we may want to do some more testing, eliminate, maybe go to more detailed integer programming, and so on. And so that is what is going on here, that it approximates these dependence problems in the real spaces, and therefore can only tell us about independence and cannot tell us about the dependence. So any questions about this general, how does it do it? Well, that's what we'll see next. But first I wanted to show you what exactly it is trying to do. Again, what it will do is it will take these spaces, take these constraints, and find out if there's a real solution here where IW and IR are belonging to the real domain. And if it finds there is a solution in the real domain, it will tell it that yes, there is a solution in the real domain. Probably you should assume there is a solution in the corresponding integral domain as well, but that's approximation is up to you. If it, however, shows you that there is no solution in the real domain, it can be very sure that there is no solution in the integral domain, because the integral domain is a subset of real domain. As simple as that. You can see that these grid points are subset of this space which I have shown here. And so if there is no solution in like this, it's not intersecting, there's no solution in this particular space, shaded space, there cannot be a solution in the grid point here. That just cannot happen. And so therefore, it is very clear and conclusive in the independence, but it is not conclusive in the sense of the maybe solution. Okay, so if you have any further questions, feel free to interrupt, but let's go back and now check. We can see how to go about finding out whether there exists integral solutions or not. So coming back to this, we rewrite this, and our goal will be to find out this particular zero or not. So now, so if you look at this particular function 2iw minus ir minus 4, it will span different values for different values of iw and ir. It will evaluate to different values. And the question is whether it will become exactly equal to 0 for some values of iw and ir, which may be real values. That is what the Banerjee inequality tries to find out. And it cannot find out if it becomes equal to 0 for integer values of iw and ir, because then it will have to enumerate all these different iwirs. Okay, so why is this possible to do in real domain and not in integral domain? That is the question. The main reason is this, that in real domain it's a continuous function, and there is a theorem which says that especially linear functions which are convex and so on might have a 0 might have 0 if the maximum and minimum values of this particular function in the bounded sense of min-max values of x, y are on either side of the inequality. So in short, if it's a fine and a linear, which is a special case of a continuous. So this result applies to any continuous function, but of course we are interested in here in linear functions as which is a special case of any continuous function. This also applies to linear functions, and we apply it in this way, that we find out the maximum and minimum values of this particular function, and if they lie on either side of 0, then they must also have a solution at 0 as far as this particular function is concerned, because it's a linear as well as continuous function. Now, where do these particular values of max and min actually occur? And that is given by another very interesting theorem by Danzig, which says that the extremal values of these functions occur on the corners of the region or on the edges of the or on the vertices of the polyhedral enclosing polyhedron, uh, which is what we are interested in. So in other words, if we have bounds on IW and IR, they will occur at certain combinations of those bounds, and it is therefore sufficient to test those bounds as per their maximum and minimum values are concerned. We don't have to be enumerative there. And as per Danzig, we can systematically find where the maxima and minima occur, which is what we'll do. So procedurally, what we'll do is we'll take this function, we'll find its maximum, we'll find its minima, and then if the zero lies between the maxima and minima, then the f will have a zero in R, and we'll assume that there is of course, we guaranteed that there is a real solution. We will not, however, be guaranteed there is a integer solution. So we'll have to choose then how to interpret that case. And we'll, of course, choose it in a conservative sense that if we can say that there may be an integer solution, we'll assume there is one, and then we'll not parallelize it. So how can the min and max play out in this case? So maybe in such one evaluation, min value was 50 of this function, and max value of this function was 100. You can see that there is no zero involved here because we are talking about the value, min value being 50, max value being 100. There cannot be a zero in this particular interval, and therefore there is we can prove independence here. However, take another case that min value is minus 100 and max value is positive 100. Now you can easily see that between these two min and max values there lies a zero, and therefore it will realize it as per the intermediate value theorem, and there will be a dependence or maybe a dependence here because of the real value solution here. Okay, so now on to the next step, and this is where we apply to find out the min and maximum values to find out what is going on in the function. So let us look at this function, a simple function f of 3x minus 2. And we have here the domain closed interval a comma b, and we want to find out what is going on about the minimum and maximum values of this particular function given certain constraints, let's say. So if A is less than B, then you can see here that the minimum and maximum values here pan out to be 3a minus 2 is less than 3b minus 2. So you can see that by putting a here, the value that we'll get applying the lower bound will be 3a minus 2. So that will be our min value. And the max value will be 3b minus 2. And that's how we'll get those. But things are more complicated than this simple example. And here is how we do the min and max computation of any function using Danzig's way of doing things. So I'm going to actually to get around some of these notations which might unnecessarily complicate things using a very simple intuitive way of calculating these values. So let's go to and do it on a simple example of a particular function here. Okay, so now let's take this simple example, 3x minus 5y minus 7. This is our function, and let's say this is sort of a doubly nested loop, or x is bounded here by 1 to 100, and y is bounded here by 1 to 300. Okay, so now this is our function, and we want to find out, of course, this is equal to 0. Is the question. We have formulated this as whether this 0 lies between the min and max values of this function. That's what we are trying to find out. So let's find out this f. F min is the minimum value of this function. How do we find that out? That's the question mark. So we simply look at you can see intuitively, if you want to maximize the value of this function or minimize the value of this function, sorry, is that whatever are the positive coefficients of these functions, their corresponding counterparts will choose their minimum value. So here we'll take the minimum value of x to minimize this function. However, negative coefficients, whatever they are, will take the maximum values of those counterparts. So what we'll do here is simple. To minimize this, we'll choose what x is allowed to vary between 1 and 100. So we'll choose 1 because that's the lowest value here, which allows us to minimize this. Now we want to minimize this, so we must choose this negative coefficient of 5. So y's value, however, we should choose as the maximum one. That's what we did, and the constant is a constant anyway. So if we do this, you can easily see that this will become some big negative value here, 1500 something. Okay, 1504 probably. Okay, so this will be the f min value. So how are we calculating this f min? We have a very systematic procedure. We traverse this formula. We look at the coefficients. The coefficient, if it is positive, we go to the variable and we choose the maximum values for, minimum value for that variable because it's the positive one. If the coefficient, however, is negative, we'll choose its maximum value, and that's basically how we'll operate. If we had to choose the maximum or find the maximum value of this variable, however, we'll do the reverse. So we'll take the excess maximum value here, positive coefficient, we'll choose the maximum value, which is 100. Minus 5, we'll choose this minimum value, which is 1. And then minus 7. It remains what it is, constant. So again, excess value, since we are maximizing, we'll choose as maximum, which is 100. Value, because we are maximizing and this is negative, we choose as the minimum, which is 1. And then y is this constant is a constant. Now this you can see it is a 300 minus 5 minus 7 minus 12, something like that. So this will give us some 288, which is positive, and this will give us this. So now you can see that 0 lies between the closed interval minus 1504 and 288, one minus value, one positive value. And so as for Banach inequality, there is a solution in the real space to this particular function in the bounded sense of its domain. And therefore, there is a dependence. There is a maybe dependence because it only proclaims it that this is a real solution. Okay, so this is formalized in terms of how do we calculate this by using C plus, C minus, all these coefficients, their positive counterparts, negative counterparts, but the intuition is simple. Whenever we want to maximize, we want to take the positive coefficient and multiply it by the minimum value of the corresponding variable, and the reverse in terms of the negative coefficient and so on. So This is how we'll calculate, and we'll find out if the extremal values of this particular function. So now let me go back and we'll continue this over here. Okay, so this is formalized here as x plus is equal to x. That is the coefficient they are talking about. If x is greater than equal to 0 or 0 otherwise, x minus is equal to x if x is less than 0 or otherwise. So you can see that these are being used here for as a notation. So here is the thing, how we find the Cx plus D, which is what we are doing using x min and x max, which is the domain's minimum and maximum values. So what we'll do is, for maximum value, we'll use the positive counterparts of these coefficients. So in other words, C plus will tell us the absolute value of C here, and in that, if C happens to be positive, we'll be using the X max here in short. If C happens to be negative, however, we'll be using, in this particular case, X min. That's all it says. One of the C plus and C minuses will be 0. So if, for example, if it's a positive coefficient, then C plus will be equal to its absolute value, and C minus will be 0. However, if C is a negative coefficient, let's say -5, then C will be positive, which will be 0, and C minus will be its -5 as the value. And then that will basically choose accordingly the corresponding coefficient. So it's just a notation here. I hope it is clear as per the definitions above. And the minimum values are also found exactly same way. And if you get confused by the notation, just follow what I said, that if it's a positive coefficient and if we are trying to maximize, then choose the maximum value of x. If it's a positive coefficient and we are trying to minimize, choose the minimum value of the corresponding thing, so that we minimize that contribution and reverse for the negative values. So we'll do this and we'll find out this particular values, and we'll find out if C lies within this or not. And this can get a little bit complicated in terms of some things in which the values are sort of interdependent. For example, the constants here in this particular case are 1 and n, so for I. However, for j, you can see it is from 1 to I. So how do we do this particular kind of case in which the constraint on one particular variable is in terms of another variable, like a triangular loop? So we would do it is we would apply these constraints using independent variables and then substitute the dependence variables and simplify them. So let us look at it here. And this is the same example. So objective function again, the dependent system that has been set up is 3i minus 4j plus 3. And I is going from 1 to n, and j is going, however, from 1 to I. So first what we'll do is we'll solve the dependencies, the system by maximizing and minimizing over j, keeping I fixed, because j is the dependent variable. And then we'll substitute the independent variables bounds and solve it further. So if we do that, and let's take the maximization of the 3i minus 4j plus 3, subject to the fact that if we want to maximize it, where j is varying from 1 to I. So in this particular case, you can see that the coefficient of j here is negative, and therefore we'll choose the smallest value of j here, keeping things simple. And of course, 3i remains 3i, but we substitute for j here by its minimum bound, which is 1. So that will make it 3i minus 4 plus 3, so which will be 3i minus 1, okay? Because we have substituted j is equal to 1, so minus 4 plus 3 is equal to minus 1. So 3i minus 1 is the maximum value of this function. The minimum value of this function will be obtained by using the highest value of j in this particular case, because it's negative coefficient. So this will be 3i, and then there will be minus 4i over there, and then plus 3. So you can see that if we substitute it that way, it will be 3i minus I. There is a typo here. No, it's not minus 3i, it's 3i. It's just an I. 3 minus I. So now if we do this further substitution on I, that we are going to put the bounds on n, you will see that if we take the first one, that will be 3n minus 1, straight away substituting I for the maximum value. And then the minimum value here will again be substituted as the min value of I over here, which will be 3 minus the value of I, which is equal to 1, and that will give us 2. Again, I think there's a typo there. Ignore for the moment the minimum calculations. I think there are some problems there. But just the maximum calculations is 3n minus 1, and I'll put some clarification on the minimum values here. They don't seem to be right. So anyway, so this is how we'll calculate the min and max values in terms of these variables, first by solving for j and then solving for I. So what is finally Banerjee inequality? The Banerjee inequality is main contribution is that we want to find out the real domain values for these functions, and if they are able to embrace 0, then we know that there is a solution in the real domain, and if there isn't, then obviously it's in the real domain, which also implies the independence in the integer domain. Now, this is one way to approach the Banerjee inequality to determine whether the dependence exists or not. Going a little bit forward and skipping some of these, let us look at, we'll come back to some of these later, but let's look at an alternative test here, which is very, very important. And that's one thing which we should look at before we get into one of the papers that I have put in there. Okay, so again, what were we doing? We were looking at something like 4x minus 3y minus 7 equal to 0. Okay, or rather this type of a test. wherein x is bounded from 1 to, let's say, 100, and y is bounded from 1 to 200, something like that. Now, if you focus on this, and we use the Banerjee inequality, and we found out there is an independence, that's great. We are done. The cost of finding this dependence or independence is quite cheap, because we are just trying to find the maximum value, as I said, by using positive coefficients with the maximum value, negative coefficients with the smallest value, and vice versa for the minimum value, and then just checking if 7 lies within bounds of this particular function or not. The minima and maxima, the bounds of minima and maxima or not. If it doesn't, then we know independence. And that's as far as the relaxation of real domain into a integers domain is concerned. But let us look at a simple example, which may be something like this. 4x minus 2y is equal to 5. Now, if you really look at this example very carefully, what is going on is we can change this particular example to 2x minus y is equal to 5 by 2. So you can easily see that we took a GCD here, which is 2, and moved that around here. Now, if you simply focus on this particular left-hand side of this, you can see that this is x and this is y, right? So these both are integer values as per the definition. And so if you find an integral function of this, okay, which is in the linear form, an integer function always maps this into some z. It must, because the space is closed under addition, subtraction, all these things, multiplications. There's no division here. So the space of integer operations is closed under plus, minus, and multiplication, which are important here. So in other words, this must evaluate to a z, positive or negative. And we don't know if it is always evaluate to plus, z plus, that's why I said z. So it could be positive or negative, but it will be an integer always. Now you can see that this one, however, is not a z, right? So what can we say then? If this is equal to z and this is not equal to z, then this particular equality has no solution in the integral space. In general, we did not say bounded or unbounded. Remember that. This, we just focused on this equality. We did not pay any attention to this. And just purely looking at this equality and doing GCD and all that, we concluded that because 5 is not divisible by 2, this does not belong to z, whereas this being closed under plus, minus, and star will always belong to z. And since this will be always integral and this cannot be integral, there cannot be a solution to this. Now this particular test is very, very useful, and it's called as GCD test. So what does the GCD test do? It simply takes the GCD of the coefficients of the left-hand side and sees if that divides the right-hand side or not. And if it does not divide, then it says independence. And if there is no solution to this integral solution in the unbounded sense, that is without talking about x is bound or y is bound, there will not be, of course, a solution in the bounded sense, because this is a subset of this. So GCD test simply worries about unbounded integral solutions and claims that if GCD does not divide the right-hand side, there is no unbounded integral solution, and therefore, by implication, there is no bounded integral solution, and therefore the dependence is independence. Now, what about the top example, which I started writing? In this case, the GCD will become equal to 1 and it will divide 7. So the GCD test says there is an integral solution to this. However, it may be that that integral solution lies in a space outside of the bounds. So that's why GCD test also cannot be conclusive. It can only tell us whether a unbounded solution exists or not, and when it does not exist, it is conclusive. If it says that an unbounded solution exists, like in the top example of 4x minus 3y equal to 7, the GCD dividing by 7 by 1, there is an unbounded integral solution to that equation, but there may not be a bounded one given x and y's constraints. So that's why GCD test also fails when we have a situation of exact dependence testing. So GCD test in short proves an independence when the GCD cannot divide, and otherwise it's to our imagination what to do with it, saying that there may be a dependence, or in fact there is an unbounded dependence there for x and y values. Now you want to use it for declaring, approximating it as a bounded dependence. That's up to you. So both GCD and Banerjee are inexact tests when it comes to proving dependence. They cannot become 100% sure. One says there is a dependence in real space, so we approximate it to the integer space. That is the Banerjee test. The second one says there is a dependence in the unbounded integer space, and you approximate it to the bounded integer space. And so therefore both have problems, and so real dependence we may not get using these particular things. Now the question is, first of all, for our problem of parallelization, how much of this approximation is really an approximation in each case? So it's well known that in the GCD test the approximation is pretty significant, because all you're talking about is a small part of the polytope here, and there we are talking about negative values of x, negative values of y, and big values of x over 1000 or 100 or 200, and so we may get dependence there which is detected by that particular test, and there'll be a big approximation. Like for example, just to sort of draw it here, this is our, again going back, this is our grids, which is our bounded integral space here. Okay. Whereas the GCD test might declare some dependence here, that there might be some xy pair here. This is my x value, this is my y value, wherein that particular function might cross that grid point, and that's where it will declare a dependence. So you can see that that space, this point could be here, 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 even negative values, and all the infeasible values of this. There could be, this line might cross here or here or here. So there could be a fair amount of approximation used here that could result here. So GCD is very approximate in terms of declaring false dependencies. The question is, so Banerjee, however, is going like this. Remember, this grid point is here. And so it may not cut any grid point here, but it might, of course, have these real values, which might be on this line. And the question is this, that does it, when it declares a real value, does it really imply a z value? And how many times does it, and how many times it doesn't? And that remains an open question. And in the next lecture, we will look at only a result of a particular paper which answered that question, which is called as I-test. It was presumed that the Banerjee inequality is, historically, it was presumed that the Banerjee inequality was extremely approximate that many dependencies are falsely proclaimed and they don't exist. They exist in real spaces, but they don't exist in the integer spaces. But this is one paper which put down the conditions in which this implication is true, is assertable. And we'll look at the result of that paper. And then empirical studies showed that, in fact, pretty often than not, this implication is true. So in short, it showed that the Banerjee inequality is able to get to the true dependence by using the real domain approximation. So we'll stop here. If you get a chance, please review some of these Banerjee inequality and other topics from the book chapters material I have I have given, so that, and if you have any questions about, because there are pretty mathematical concepts here, they are not difficult at all, and hopefully all the clarifications of finding the extremal values of functions, etc., are fairly simple. But go ahead and review it, because then you will understand the implications of the paper very clearly. That we'll talk about. We'll only talk about the main result. We'll not talk about the proofs, of course. So with that, we'll stop here. Thank you, and we'll see you in the office hours if anybody has any questions. And again, hopefully the project extension will help. And we are going to assign the last homework, which will be mainly based on all these Banerjee inequalities and loop transformations, which is the next topic, which we'll cover quickly in the next week. It will be mainly based on these tests. There are many, many tests, by the way. I have covered only 2 important tests. There are, as you can imagine, all kinds of variants of integer linear programming tests. One of the prominent ones being Fourier-Motzkin, but we will not discuss those, because end result of all this is that it is okay to just use Banerjee inequality, and that's the result we'll focus on. Thank you, and see you then.